Good morning, everybody. Uh, we've been talking about astronomy with the naked eye and some of the things that you can observe that way. Why do we use telescopes? That's the topic for today. How do telescopes work? What are they? And why do we use them for astronomy? And before we get to that, how does your eye work? Because there's really not that much difference between the naked eye and a telescope. The job of your eye is what? Light goes in your eye, light shines toward your eye, it passes through the pupil of your eye, that light passes through the lens in your eye, and the lens in your eye bends the light and focuses it onto the retina of your eyeball. The retina of your eye then absorbs that light, turns it into information that gets carried by the optic nerve to your brain, and then your brain sees what your eye sees. This is essentially the same thing that a telescope does. Light comes in, that light gets focused into a focused image, a clear image, and then the image gets recorded somewhere in a photograph or a spectrum, or in the case of your eye, your brain. It gets recorded as a memory in your brain. And our eyes work wonderfully. But it does have some limitations that limit our ability to do astronomy. For one, our eyes are only so big. And if you want to see something really faint, it would be nice if we had a larger aperture to absorb the light through to make faint things look brighter. We have no ability to soak up light over an extended period of time. Our eyes can't take a long exposure. In order for us to see motion and change, our eye is constantly updating our brain with what it sees now, what it sees now, what it sees now. And so our eye does that. Our eye signals our brain about 25 times a second. So our eye can only soak up light for 1/25th of a second before that information gets carried to the brain. If you're looking at something really faint and your eye doesn't absorb enough light in 1/25th of a second to really signal anything, then your eye sees black. If you could take and soak up light over an extended period of time, if you could really absorb light for several seconds, then something would show up and you wouldn't just see black. That was one of the huge innovations of photography, where with photography you can take a longer exposure, expose that film, soak up light so that it makes everything look brighter. Our eyes can't do that. Our eyes have a fixed magnification and a fixed field of view. Our eyes can't zoom in and zoom out to make things look bigger or smaller. Our eyes always see the world the way our eyes see the world. So if you wanted to zoom in on a patch of sky or a part of the world and make it look bigger, you would need optics for that, right? You would need some device, hence telescopes. And our eyes have a small wavelength coverage. What I mean is, our eyes can only see visible light. There's all these other kinds of light, right? Our eyes can see red, orange, yellow, green, blue, violet. But there are other kinds of light, like infrared and ultraviolet and radio waves, that our eyes cannot respond to. They are invisible to us. They're still light. It's just not the light that our eyes react to. And so if you wanted to see what the universe looked like in infrared light, you would need to build a device that can do that. And so we have. But you can't do it with the eyes. So our eyes work great to a certain extent. If you want to do something beyond the scope of which our eyes evolved, then you would need some better devices. And that's where telescopes come in. There are two major designs of telescope, but they fundamentally have the same job. Collect light, focus that light into a focused image, and then shine that image somewhere useful. And you can do that with reflecting telescopes use a mirror to do the collecting and focusing, and a refracting telescope uses a lens. And originally, when telescopes were invented in the early 1600s, lenses came first. Lenses were invented before high-quality concave mirrors. And so people realized that if you take a lens, if you take a piece of glass and polish it to just the right shape on both sides, then light will pass through that lens, come to a focus, and this is how spectacles, monocles, magnifying glasses were invented. And then shortly thereafter they realized, well, if I put a second lens here, I can combine the power, I can combine the ability to refract and bend light to create a clearer, more magnified, more focused image shining into my eye. In a refracting telescope, the main lens that's doing all the collecting is called the objective lens, and the second lens, where the clear image shines out of into your eye, is called the eyepiece. After, about 100 years, people realized that you could do this exact same thing, but with a curved concave mirror. So they started combining mirrors and lenses to create reflecting telescopes, where light comes in, just the open hole of the telescope tube, light comes in, bounces off the curved concave surface of this primary mirror. You could call it a primary mirror, or you could call it an objective mirror to compare it to an objective lens. The light bounces off the primary mirror and it starts coming to a focus, and so you stick a secondary mirror in there to the job of the secondary mirror is mostly to just bounce that light somewhere useful, like off to the side here, so that then that image shines through the eyepiece, and the eyepiece, just like it does in a refracting telescope, the eyepiece does the final magnifying, the final focusing, and then you put your eye up to the eyepiece and a clear focused image shines into your eye. Everything else about a telescope is just details, right? There's lots of bells and whistles and choices that you can make to design the right tool for the right job, but everything else is just details. A telescope's job is to collect light, either by a objective mirror or an objective lens, focus that light to a focused image, and shine that image somewhere useful, either into your eye or into your camera or whatever's recording the information. One of the important pieces of information to know about a telescope is the focal lengths. So the focal length of any lens or mirror is the distance from the lens to where that light comes to a focus. So the starlight enters the primary lens, the objective lens, two ways of saying the same thing. That light starts bending toward a focus, and once it comes to a focus, that light comes to a focus here. So the focal length of the objective lens is this length here. In order to make a better image, we let the light come out of focus, shine into the eyepiece, and then the eyepiece also bends the light, and the image shines out of the eyepiece. So this is the focal length of the eyepiece, the distance from the lens to the focal point. The image that you see coming out of your telescope is produced by bending light by the objective and the eyepiece. So we need to know the focal lengths of both lenses to understand the image that we're seeing produced by both. All right, so that's the first important property of a telescope to know, is what are the focal lengths of the objective and the eyepiece lens, or mirror if you're using a reflecting telescope. The other important property of a telescope to know is the diameter. Right? Those are the two most important things to know that define what kind of an image your telescope is going to give you: the focal lengths and the diameter. All right? Why do the focal lengths matter? Because the focal lengths of your two lenses explain the magnification. What is magnification? Magnification is how much bigger an object looks in your image than it looks to the naked eye. And so one thing that lenses and telescopes can do is make small things in the sky look bigger. The sun, the moon, planets, nebula, galaxies, they all can be made to look larger based on how the light is bent and focused by those two lenses. Pardon me. FO here is the focal length of the objective, FE is the focal length of the eyepiece. So if I take two lenses, if I take a lens with a 1250 millimeter focal length, and I use that as the objective, and then I grab an eyepiece that has a focal length of 25 millimeters, what kind of a magnification would I get from that combination? If I take the focal length of the objective and divide it by the focal length of the eyepiece, 1250 divided by 25 is 50. So I would get a magnification of 50 times. Which means what? It means whatever I look at, anything that I look at with this telescope will look 50 times bigger than it looks to the naked eye. When you look at really small things and you magnify them to look bigger, you want to measure the size of something. But what is the sky? Right? The sky is a dome, right? The whole sky viewed from Earth is a celestial sphere. And so when you measure the sizes and the distances between things on the celestial sphere, you're measuring angle, right? The angle from one object down to the Earth and then back to the other object. And in astronomy, these angles can be very small. Right? For example, the width of the moon, the width of the full moon, the angular width of the full moon is about half a degree. Right? Now, the full moon is one of the biggest things in the sky, right? The moon and the sun, the full moon and the sun are about the same size, which is how we can get total eclipses. But they're only half a degree, which means, what do I mean? I mean that the angle from the left side of the moon to your eye to the right side of the moon is half a degree wide. Now if you start looking at even smaller things, then the angles get really, really small, and then it becomes annoying and cumbersome to be juggling these fractions of a degree. So we don't do that. What we do is we break a degree into smaller units. We take 1 degree and break it into 60 subunits called arc minutes. And so I could say, well, how big is the full moon? Well, the angular size of the full moon is half a degree, or I could say 30 arc minutes. And 30 is usually a more convenient number to deal with than half. But for really small things, even an arc minute is too big. And so then we need to break that into even smaller units called arc seconds, and then you can measure the size of really small things in these arc seconds. So you can think about these angles as being a lot like time, right? 60 arc seconds in an arc minute, 60 arc minutes in 1 degree, and 360 degrees makes a full circle all the way around the Earth. When we make notations of these angles, degrees are the little circle like usual. 1 tick mark is the note for arc minutes, and then 1 arc minute is 60 arc seconds. So the 1 tick mark is arc minutes, the 2 ticks, the 2 apostrophes is arc seconds. When would we use this kind of notation? When would we measure these kinds of angles? Well, we would measure with those angles when you're doing things like measuring the field of view of your telescope. These are 2 images of the same object. These are 2 images of the Eagle Nebula, but they're with different magnifications, right? Both of these images are centered on these pillars of gas here. That's these same pillars of gas over here. But this image on the left is 7 arc minutes wide, whereas this image on the right is only 1 arc minute wide. So these are 2 images of the same object, right? The nebula hasn't gotten bigger or smaller. The nebula is however many light years big that it really is in the galaxy. We're just looking at it with 2 different magnifications. In this image, we've magnified these pillars of gas to look bigger, but there's a trade-off, because when you zoom in to make small things look bigger, your field of view gets more narrow. I can only see 1 arc minute wide on this image. All the other arc minutes, all the rest of the nebula is outside of the field of view. So you always, like I said a minute ago, you want to pick the right tool for the right job. Do you want to have a narrow field of view and make something small look bigger? Or do you want to see the whole nebula? Do you want the wider field of view? Well, then you would pick the lenses. Then you would pick the lenses that would give you a lower magnification for a wider field of view. All right, so that's why the focal lengths of the eyepiece and the objective are important. You want to pick the focal lengths that give you the magnification and the field of view that you want, depending on what object you want to look at in the sky. The other major property of a telescope to know is the diameter of the primary mirror or the objective lens. That's what I mean by diameter. For example, these are a couple of pictures of the Mayal telescope on Kitt Peak. The Mayal is a 4-meter telescope. Is it 4 meters long? No. The length of the telescope tube really doesn't matter. That's just details. The very most important thing to know is the diameter of the mirror. Right? This is the primary mirror. It is 4 meters in diameter. So the length doesn't really matter. It's the diameter that matters. Why? Well, because if you have a wider mirror, you've got a larger area to collect light with. Right? Let's say you have a 1-meter mirror versus a 10-meter mirror. Right? That 10-meter mirror is 10 times the radius, 10 times the diameter, of the 1-meter mirror. And if you remember your geometry, you'll remember that the surface area of a circle depends on the radius squared, right? So if you have 10 times the radius, you're going to have 10 squared times the area. What's 10 squared? It's 100, right? All you got to do is get a mirror 10 times larger, and you have 100 times more area to collect light with, which means you're going to be able to collect 100 times more light per second. And all of a sudden, everything in the sky looks 100 times brighter. And when you can do that, you can make faint things visible out to much greater distances. So having a larger diameter mirror makes everything look brighter. For instance, here are 2 images of the Andromeda Galaxy. These 2 images have the same field of view. This one is taken with a smaller mirror, right? With a smaller mirror, you can't collect as much light. And so all you can see is the bright stuff. All you can see are the bright parts of the galaxies. But if you have a larger mirror, with a larger mirror, sure, the bright areas look even brighter, but now you can make out the faint areas, right? These faint limbs, these faint arms on the edge of the galaxy now become visible because you've got a telescope with a gathering area, with a light gathering area large enough to see even the faint stuff. Having a larger diameter mirror gives you another benefit, and that is resolution. Okay, so this is a little bit more confusing, so let's break this down. All right, when you talk about the angular resolution in of an image, what you're talking about is the resolution is what is the smallest detail that I can see? What is the smallest detail that I can make out in my image? So let's say, for example, let's say you're standing on the side of the highway, you're walking at night. Don't know when you would do this. Probably shouldn't be standing in the road, but whatever. Let's say you're standing on the side of the highway late at night, and there's a car coming toward you over the horizon. Well, when that car is still on the horizon, you're just going to see one light source, right? Because why? Because the left and the right headlights are so close together in angle, right? The headlights are the same distance apart in meters, but when that car is really far away, the angle from the left headlight to your eye to the right headlight, that angle is too small. Your eye can't tell those 2 headlights apart. It just looks like one headlight. And then as the car gets closer to you and closer to you, the angle between them gets bigger until eventually that angle gets large enough that you can clearly resolve, oh, that's 2 headlights. Right? The angular resolution is the alpha right here. Alpha is a measure of what is the smallest angle that you can make out. What is the smallest angle where you can see that that's distinctly two headlights. This resolving angle alpha equals 12.5 arc seconds, right? Two apostrophes is arc seconds, divided by the diameter of your objective lens in centimeters, right? So as the diameter of your objective lens or primary mirror gets bigger, you're dividing by a larger diameter, that means the angle alpha gets smaller. If alpha gets smaller, that means you can see smaller and smaller details. And you can make out finer and finer lights and light sources and details in the image. Right? So, for example, you might pull out your telescope and you'd look at a star and you would say, yep, that's a star. I can see it right there. But then if you look at that exact same star with a larger diameter mirror, you would look at that star and you would see, oh no, it's actually two stars. Right? Those two stars are so close together in the sky that with my small telescope, I can't see the difference between them. I can't see that level of detail. I have a larger resolution angle where I can see large details, right? This is where it gets a little bit confusing, right? Larger resolution means you can see larger details, but not small details. But if you use a larger mirror, you have a smaller resolution. You can see small details like the fact that, oh no, that's two stars right next to each other. Right? Here's a few images of Andromeda again. Right? These images are the same magnification, same field of view, but they're taken with different diameter mirrors so that you have different resolutions. Right? This one will have the large resolution, right? I can see these big details, but I can't make out the small ones. And then as you go to B to C to D, you're able to see smaller and smaller details. So smaller resolution means you can see smaller details, so the image is clearer. For astronomy, having a larger diameter mirror or objective lens is almost always better, because if you have a larger mirror or lens, it's a win-win. You get both a larger light gathering area, so everything looks brighter, but also you have a smaller angular resolution so that everything looks clearer. Pick the right tool for the right job. Right? Pick your mirrors and lenses so that they have the magnification and the field of view, as well as the brightness and the clarity that you need to see the object that you want to look at the way you need to. This is the main job in astronomy, is to work backwards. Say, I'm interested in studying this object. I'm interested in studying the moon or a planet or a nebula or a galaxy. And given that this object is this far away and it's this bright and it's got this much detail to it, would it be okay? Right? If you were just wanted to take a pretty picture of the moon, well, the moon is really big, so I would need low magnification and a wide field of view to take one picture of the entire face of the moon. And, I'm just taking a pretty picture of the moon. I don't need a giant mirror because the moon's plenty bright as it is. And if I have a small mirror, I'm going to have a measly angular resolution, but, I'm taking a picture of the whole moon. So having a small mirror is fine. And I'm still going to see the light and dark areas on the moon just fine. But if you're talking about some object that is really small and really dim and really far away, well, then you need a high magnification and a large diameter mirror to make that faint thing so far away look brighter, and so that you can clearly make out all the details in that galaxy or that nebula. This is why every telescope in the world is a little different. I said at the beginning, oh, that's details. Well, yeah, it's the details because all of these telescopes in the world are a little different. Different mirrors, different lenses, because they're built with a specific job in mind. Some telescopes are made to study galaxies. Some telescopes are made to study planets, so that if you're an astronomer that wants to specialize in studying planets, well, now you know what tool to go work with. Right? You could try and study planets using a telescope designed to study galaxies, and well, we have, right? I mean, there's lots of gorgeous pictures of the planets using the Hubble Space Telescope. It can work. It's just not going to be the best use of your time and your money and your energy, right? The Hubble Space Telescope was designed to study galaxies, but it can do some great work with planets also. It'll work. It just may not be the best, the most optimal. Decide what your program of study is, pick the right tool for the right job, and there's your telescope for you. Okay, I hope that explains some of the details of choosing the telescope that you want. Have a good morning, everybody.